were at this point, right? The initial equation was this quadratic equation, right? That gives us the two values of r, and with the largest, 2, the smallest was -1. And this was the recursive formula, n plus r times n plus r minus 1, Cn plus n plus r minus 1, Cn minus 1 minus 2Cn equal to 0. And this was valid for n starting at 1, right? And we're looking for a solution. Originally we started, I'm not going to write down like this, right? N plus r. So, in order to find the two, in this case, the two linearly independent solutions, right? Power series solutions, y1 and y2. This is, once you always end up with a quadratic equation or in the case of, this was a regular singular, right? Remember the definition we gave last time for this, right? Then the method of Frobenius applied, and we started, and you always end up with a quadratic equation that will give you two values of r. In this case, we get the largest, you call it the r1, and the smallest, the r2. So, now, depending on the nature, on what those numbers you end up with, there are three cases to differentiate, right? Three cases. Let me just put them here. So, cases to be considered depending on, first, if the difference between these two is not equal to, is not positive integer, 0 or 0, then you get two solutions. The two linearly independent solutions, right, are the first one with the, when you put, and the second one, you will find the other coefficients for the R2, right? So, what would you do? What would you do to find those two? In this case, number one, you plug the first one, the first value of R1 here, and find the CNs for the first one. Plug them in the first one. Then you go to the second value, plug it here for R2, and that's how you find the ones with the tilde, the other coefficients for the second one, right? You plug them here and you get the two. That's case number one. This is the simplest case. There are three cases to consider depending on the nature of these two. Now, as you can see, the example we're working on, we get these two values, right? These two, so no, the first case is when this is not equal, right? It's not a positive integer, or 0. Now this is not case one, because what's the difference? When you take the difference between these two, you get 3. So it's a positive integer. So it's not a case one, it's a case 2, that's the second case. If the difference is a positive integer, either 1, 2, 3, then what happens? Then you get this to be the first, always the same. But the second one might or might not have an extra term. In this case, because we're taking x minus the x. But if x0 is 0, so let me just take x. And where C could be either 0 or not 0. Meaning, you first try, assume that this is 0, that there is no extra term. And if what you get here is different from what you get here, then you don't have this extra term. But if when you assume that the constant is 0, that means that this is not here. And you work out finding the C and tildes with the R2 in case 2. Whatever you get here is the same as this, they are not linearly independent, then the assumption is not correct and you need to add an extra term. Where this Y1 is whatever you found up here, it's another power series. And that's when things get really complicated, not in the sense that finding the coefficients of the second power series is more time consuming, right? And finally, the third case is the remaining, right? When the two values of the R's are equal. In the solution of the initial equation, the quadratic one. Then, what are the two linearly independent solutions? Then in this case, you get this extra term. Always. Okay? And that's when finding the second linearly independent solution becomes a more complicated. So you get this R1, the two are equal, so this is the R1 and the R in the case number 3, right? Any questions?
So, case number 2, it refers to the element, correct?
To the?
Element, like if R1 minus R2 is equal to 1, 2, or 3.
Then the two linearly independent solutions will be, the first one is always the same in the 3 cases. But the second one in case 2 would be this with an R2 here, of course. And you might or might not have, when this thing might be either equal to 0 or not equal to 0. So you first try the simplest case when it's 0.
Yeah.
If when you assume that this term is not here for the Y2, in case number 2, you get something here which is linearly different from this, then the assumption was correct, and you don't have this term on the second solution. But if when you assume that this is not here and you work out the recursive formula to find this one, you end up with this to be the same as this, then they are not linearly independent. So what's the problem? The assumption we made is not correct, so now you need to have this extra term and redo the problem to find the C and tildes so that this, with this Y1 now being that one, you always first find this one. And then finally on case number 3, when the two values in the two solutions of the initial quadratic equation come out to be the same, then this is this, and this is always here. There is always this extra term with a Y1 times the logarithm. And that's when finding this second linearly independent power series solution is really time consuming, because finding those coefficients, you have that extra term with the logarithm, making things more difficult. Not the first one, but the second. Any questions?
So the third case doesn't have a constant n, like you're not plusing
Class,
constant.
you always have this. In the second case, there was a seed that would not be zero.
Yeah.
But in the third case, when the two values of R are equal, you always have this extra thing. So the constant is 1.
What's the website on the board?
Huh?
What's the website?
No, this is a website for
I'll show you later.
a calculus, a limits calculus 1 application. It's like a computer game,
Oh.
3 dimensions, really cool.
Yes.
Wait, so you're telling me that in case 3, I'm always gonna end up with 3 power series in my final general solution?
No, not 3 power series.
But
You get this one and the